Today's topic is complex analysis. How we're going to take a complex function over a complex domain. The reason why we study about this one is to taking inverse Laplace transform. We know that the Fourier transform and Laplace transform, let's review some of them. The Fourier transform of a function xt is defined as a the whole time xt is integrated by the product of this basis function. Okay, this is the Fourier transform. The inverse Fourier transform of this one can be expressed in this way: 2 pi times integral x j omega e to the j omega d omega. Okay, from here we call this one is x j omega. At here we take the integration over time. Okay, we take the integration over time, the whole times. So xj omega is not a function of time anymore. It's only function of omega, because we take the integration the whole time range. It's the same. We take the integration over omega. Okay, the whole omega section is integrated. Now the t is remained as a function. So this is the inverse Laplace transform. What about the Laplace transform? Okay, look at the Laplace transform. In the Laplace transform, we take a Laplace transform expression like this one, and we express s as a complex number, like s is real plus imaginary terms. Real term is a sigma, and the imaginary term are j omega. And this is defined as this way: integral compared to the Fourier transform, and the xt is integrated with this basis function s. Okay, st, but s can be decomposed as sigma t and minus j omega t. So it's quite similar to this one, Fourier transform over xt. Okay, it looks like this one. Then by use of inverse Fourier transform as shown here, we can define the inverse Laplace transform. By use of the inverse Fourier transform, we can express xt e to the minus sigma t equals to 1 over 2 pi infinity to infinity. And we know that this one is okay, this one equals to this one. So we can xs is added here, and see that e to the j omega t d omega. Okay, from now on we can multiply e to the sigma t both sides. Then inverse Laplace transform are defined in this way: xt equals to 1 over 2 pi and integral infinity to infinity, and xs, see that e to the if you multiply this one will be sigma plus j omega t. That's the st. st, and the integration variable at this moment is omega. So we need to d omega. I would like to replace this one. This d omega part should be replaced with the ds integration. But we know that s equals to sigma plus j omega. That's why if omega changing from minus infinity to infinity, okay, then s will change in sigma minus infinity to sigma plus infinity, okay. But at here we know that the ds equals to j d omega. That's why d omega are given as ds over j. Okay, d omega, okay, this is d omega equals to ds over j. So I would like to replace d omega with ds over j, then it will be 1 over 2 pi j, and the integration range will be sigma. We know that it's starting minus infinity, so minus j infinity to sigma plus j infinity, and xs st, now ds. Okay, this one is definition for the inverse Fourier transform. Okay, this is definition of the inverse Fourier transform. You can see here, this is complex number. S is complex number like this one. We need to take a complex integration is required to taking inverse Laplace transform. So we need to know how to integrate the complex functions. Xs is also complex function. Okay, so we know that why we need a complex integration. From here, what is the complex function then? Complex function is a mapping from the complex domain to the another complex range. Here is the x real variable, and the jy variable is this one. This one is the g domain. Okay, this becomes the domain. Okay, by use of the function, each point is mapped to the another complex domain. This one is a range. Function is a mapping from domain to the range, but in the range, real x is u and imaginary is jv, but the u is a function of xy, x and y. V is also a function of x and y. Okay, this is complex functions, but it's not that easy to visualize. Later, I would like to show you that how to visualize the complex functions. At here, the key function when we would like to handle is analytic function. What is the analytic? If function f is analytic on a region R, it's a differentiable. Differentiation is existent at every point of the range, every point of the region. Then what is the differentiable? Okay, let's consider this kind of function is absolute value of t. Then we can plot the function over here. Okay, xt, let this is time domain, then we can express okay, okay, the function will looks like this one. If t is positive, its slope is 1, but the t is less than 0, its slope is -1, like that. This is these functions. So if we plot xt over time, this is t equals 0. Okay, this one is xt. Then xt will follow in this way. But what is the differentiation of this one. The definition of this one is a change of x with respect to change of time. If we plot of this differentiation in the positive time, if t is positive, it is 1. The slope is 1. You know that in the time is positive, xt equals to t. But if t is less than 0, then it becomes the minus 1. So, left side and the right side has different differentiation. In this case, we take the delta t goes to the 0, taking limit. But there is two different limits. One is approaching from left side to the right, this approach. So, if approaching left side to the 0, then still its differentiation value is minus 1. But what if the approaching from right side, if we approaching in these directions, it still is 1. So left side and right side limit doesn't equal. In that case, differentiation value are not exist. So it is not possible to take a differentiation. Okay, so in this case we call differentiation is not possible. So here it says that if a function is analytic, then the function should be differentiable at any point inside of the region. Okay, so the definition of analytic means related to differentiable. Okay, if the fg is an analytic function, then we can make it series expansion. So we can find out any differentiation of the analytic functions, then it's possible to take a series expansion. Okay, here is an example. The f of g is defined as g square. So g is x plus j omega. Okay, this is a domain. So by taking square, the x plus j omega times x plus j omega will give x square minus y square. That's the real part. Okay, this is the real part, and imaginary part is xy and xy. 2 times jxy is the imaginary part. F of g is expressed by u plus jv, like this way. So u is the real part of that one. Okay, this is uxy, and v is imaginary part of that. We can plot the complex function real part and imaginary part separately. Then we can make it visualize. Here shows the real part of that. So this function is x square minus y square, and this one is a imaginary part. Okay, you can see when we have to visualize a complex number, we can separately plot that one. That's the 2xy. So we define what is the complex function and what is the analytic functions. You know what? Fg equals to g squared. This one is also analytic functions. We can take a differentiation. Now move one step further. That's the Cauchy-Riemann conditions. Cauchy-Riemann condition related to analytic function, and analytic related to differentiations. Here shows that if function are differentiable, then it should satisfy the Cauchy-Riemann conditions. So it's this one. If taking function at the complex number g0, we take the differentiation. That's the definition is this one. X delta g goes to the 0, and the delta g over variation of functions. But complex function has two variables. One is x, the other one is y. So delta x and delta y, both of them should be approached to the 0. Okay, that's this one. But here shows that the complex domain, we would like to approach to the g0 in certain path. So delta x and delta y should be 0 to to approach to the g0 positions. We would like to take a differentiation at the g0. But there are two different ways. One is the already delta y is 0, then we can approach along the x-axis. So that's this part. We take the delta x approach to the 0, but we assume that the delta y already 0. So and this one is a differentiation for by change of x. Okay, we would like to take a differentiation at the g0 point by moving delta x. So that is this one. Then we can find out the f is u plus jv. Then we can apply differentiation both of the real and imaginary part. Then real part becomes partial u over partial x, and imaginary part is partial v with respect to partial x. Okay, this one is the first approach. We would like to differentiate along the x-axis at the g0 point. The second approach is taking differentiation along the y-axis. So that's this one. Limit delta y goes to the 0. So we would like to measure the difference. J delta y is change of these axes. And divide by delta y. We would like to consider this part. Okay. At this moment, we assume that the delta x is 0. Delta x is already 0 in this axis. We would like to change in this axis. Then it is defined like this way: partial f over partial jy. Okay. Then we can apply derivative to the real and image part separately. Then this will give partial u over j partial y and partial v over partial y. You know that j is cancelled out the imaginary part. But we define that the differentiable, these two values should be equal. That is the Cauchy-Riemann conditions. It says that the real part should be equal. So this is the real part when we are approaching along the x-axis. Okay. What about along the y-axis? That should be this one. So these two things should be equal to satisfy the analytic function. So to be differentiable. And the imaginary part should be also equals. To be equal, it should be like that. Okay. So partial u over partial x should be equal to the partial v over partial y. Okay, this is the real conditions of the differentiation. And the imaginary condition is opposite signs. Partial v over partial x should be equal partial u over partial y. Okay. So this one can be expressed equally in this way. So the subtracting partial u over partial x to the partial v over partial y should be 0. And adding these two terms should be 0. So this is called Cauchy-Riemann conditions. Let's consider that the fg g to the square function is satisfying the Cauchy-Riemann condition or not. We already plotted this one also. So fg is consists the real part is u, imaginary part is v, but the real part, as we know that it is given as x squared minus y squared. That's the u function, and the v function is cross product of x and y, 2 times xy. That's the v. By take the derivative of u with respect to x, partial u partial x, you can from here it's a 2x. Okay. So what about this one? Partial v of partial y. Partial. Okay, this is partial v. Sorry. Partial v of partial y is this one. Taking derivative with respect to y, it is 2x. So it is equal. So it satisfies these real conditions from here. What about the imaginary conditions? Okay, this is v. To check the imaginary part, we have the derivative of v with respect to x. v derivative with respect to x, then it will give 2y. Okay, this will give 2y. And what about we taking derivative u with respect to y? We take the derivative with respect to y, it will give minus 2y. Okay, so it is equals to minus of the partial v of partial x. So it satisfies these conditions. That's why g square function satisfies the Cauchy-Riemann conditions. It means it's a differentiable complex function.